The first exponential model we're going to look at is for increasing functions, and that's the doubling time. So the doubling time is the amount of time that it takes for a given sample to double in size. So we are growing here or increasing. Okay, and that means if we were talking about maybe a bank account that's accruing interest, if we started with $500, what we'd be interested in is the amount of time it takes to double. So that would be the amount of time it takes to reach $1,000. So 2 times as much. All right, so let's look at how we set these up. If we're using our constant or standard exponential growth, we have AB to the T. So our starting amount here is A, which means if it doubles in size, we get 2A. So you have an A on both sides that we can cancel out, and so we can jump straight to 2 is equal to B to the T. So if you're doing doubling time and you have just a constant growth rate, you could go straight to this form of the equation to work on this. And then similarly for the continuous form, that's AE to the KT. If we double our original amount of A, we get 2A. So I'll cancel those A's again. And then for this one, I have 2 is equal to E to the KT. So if I'm doing a continuous doubling, I could jump straight into 2 is equal to E to the KT in order to tackle that problem. All right, so let's look at a couple of examples. We're going to start by finding the doubling time of a bacteria colony that starts with 100 bacteria, and it grows by 30% per hour. So that 30% per hour is indicating a constant growth rate. So we'll use this form 2 is equal to B to the T. And then the thing that we're going to fill in here, we're supposed to be finding the time. So we need to find T, which means we must know what B is. So let's see if we can figure that out. We're growing by 30%. So that's my growth rate R of 0.30. And then to find my growth factor B, I'm going to add 1 to that. So I get 1.30. So I can put that into our equation. We get 2 is equal to 1.30 to the T. Okay, and then we're ready to solve this, but we have a little bit of a snag here because our T is all the way up in the exponent. So in order to bring that down, we're going to use, I'll use natural log. You could certainly use the common log as well. Either one would work. But by using that, we can use that law of logs that allows us to bring the exponent down in front of our log. So do natural log on both sides. So I get natural log of 2 is equal to T times the natural log of 1.30. And so then I can divide that over. So I get T is equal to ln of 2 divided by ln of 1.30. So that would be the exact answer. And then if we wanted to approximate that, we could put that into a calculator and get a decimal approximation. All right, so we have ln of 2 divided by ln of 1.30. So that gets us about 2.64. So we get 2.64, and our units here are hours. So our bacteria will double in size in just short of 3 hours. And then one thing I want to point out here, because we use this form, turns out there is an extra piece of information that we never used, and that's that original amount of 100 bacteria. So you would only need to use that if you started with this form that has the A's in. If you've already eliminated those or canceled those out, then you don't need this. So we didn't need that information. We were still able to solve that just fine. All right, so let's look at an example that uses a continuous growth rate. So this one says the population doubles in size every 20 years. So they're giving us a time, there's our T, and they want to know what is its continuous growth rate per year. So continuous is telling me I'm going to use 2 is equal to E to the KT, and then I know that my T is 20. So I get 2 is equal to E to the 20K. So K is what I'm solving for here for my growth rate. And then on this one, I am going to use natural log because it does actually make a difference here. ln and E are inverse functions. So when I use those, I get some nice things that happen here. So that leaves me with just the 20K. So I get ln of 2 is equal to 20K. I divide both sides by 20. what I get is that k is equal to ln of 2 over 20. So this would be the exact answer. And then if I wanted the approximation, I could put that in a calculator to get ln of 2 divided by 20. And that gives me 0.0346. Okay, or 3.46% is our continuous growth rate per year.